I hope everybody had a good 4th and yesterday. So today I want to pick up on a lot of the topics that Jeff talked about on Monday about properties of the megathrust, and I'm going to hopefully give you a more seismological perspective. So, the title Megathrust earthquakes are events that occur at the plate boundary at subduction zones. And the mega, generally we're talking maybe about events 7.5 or larger. And if we look at where around the globe these events occur, here it's showing since about 1900 all the largest earthquakes, where you see black blobs is where we actually could determine something about the rupture area. So what length and distant width on the subduction zone actually ruptured. And the bigger the rupture area, the bigger the earthquake. When there's not that information, you'll see X's. But do I have a pointer? Oh yeah, here. Is this a pointer? Okay. So you can see that along the subduction zone in South America, Alaska Aleutians, into Kamchatka and Japan, we have a lot of very large earthquakes. But you go look at the Marianas and down here in New Zealand, there's a dearth of large events. So we'll get back to that. There's also not a uniform distribution of these events in time. So here is a map again since 1900 of these large, mostly megathrusts. These are the largest events since 1900, so they show focal mechanisms. Not all of them are megathrust on the subduction zone plate boundary, but most of them are. So everything in both green and blue, but the blue, the beach balls, the actual focal mechanisms are just those events that occurred in this 10-year period, 2004 to 2014. So there's really been this explosion of large megathrust earthquakes in the last decade, and that's much more clearly shown in this plot here of magnitude of events versus a year. So, and here below is cumulative moment versus year. Okay, so we can see, let's go back in time, that late 1950s through the end of the 60s was another kind of surge or cluster of very large earthquakes. And then things got relatively quiet for a couple of decades, and then starting with the 2004 Sumatra earthquake, another kind of burst of activity that's continuing through today. Now, I did my PhD work kind of in here, in this period of nothing going on. So I spent a lot of time actually studying these very large earthquakes that happened in the 50s and 60s. And if somebody asked me, well, even asked me up until 5 years ago, whether there was some kind of, why are there these clusters? Can an earthquake that happens in Chile actually affect or bring closer to failure a large earthquake in Alaska? I would have said, absolutely not, that's crazy. Now I'm not sure how I feel about that, but there are absolutely some people who think that the seismic waves that are generated from these big earthquakes that travel around the globe actually can change the stress state at distant plate boundaries and actually bring them closer to failure, and that there may be super cycles of these earthquakes, this being one, and we're in another now. Now, I'm not going to talk more about that. It's interesting. There are some papers about that. But I am going to use the fact that we have this amazing number of large earthquakes that have occurred when geophysical instrumentation was really exploding, and that they're really very, very well recorded. And we've learned a tremendous amount about megathrust earthquakes from that data. So what I want to do today is to really try to synthesize what we've learned from studying those recent large earthquakes, and then try to discuss some, obviously we always have outstanding questions and directions for future research. But before I do that, earthquakes are a frictional process, and we've talked a lot in here, and I'm going to continue to talk about rheology, mostly kind of rheology of the deeper part of the Earth. So I wanted to spend a little time and talk about friction and its relationship to earthquakes. So it's been observed for quite a while from continental earthquakes that they don't seem to happen near the surface of the Earth. So this is a distribution, it's a histogram, so number of events versus depth for earthquakes in Parkfield. And there's maybe a few events near the surface, but in general, earthquakes don't seem to start in the continental crust. And this is still kind of true today till maybe 3 or 4 kilometers. And then, you kind of have some kind of distribution, a peak, and then they end in continental crust somewhere about maybe 15 or so kilometers. And that's analogous in subduction zones. Here's a little cartoon of a subduction zone that we also don't observe many earthquakes happening shallower than maybe 10 or so kilometers below sea level. And we have a lot of earthquakes in I'll term the seismogenic zone, and then we transition again out, not having earthquakes. So we see an analogous transition. And so, we see some kind of aseismic behavior, which is believed to be, stable sliding. We know the plates are moving, so we're accommodating that motion somehow. Creep and stable sliding, transition into some kind of unstable seismogenic zone, and back out. So, let's see okay, so these are frictional transitions, and this man was very important in doing a lot of experiments on friction and helping us understand these types of transitions. And again, in the spirit of famous scientists. Oh, you're right, but oops, I'm sorry, laser. But I thought we have students and postdocs answer. Okay, he's just proud that he knows, right? Because but does anyone recognize who this is? Yes, okay, yes. He worked at the USGS, and he did a huge number of experiments on friction. And these experiments were very similar to the rock deformation experiments that have been talked about, except when actually putting the rocks under normal stress, there was a kind of a cut already made in it so that slip would occur and failure on a pre-designated surface. So he did experiments basically under different normal stresses and applied shear stress and saw how much shear stress it took for failure. Okay, so here's normal stress, shear stress on the y-axis, normal stress on the x-axis, and what he found, and this is called Byerlee's law, okay, that there's a linear relationship, and that the slope tends to change, that this coefficient in the shallower parts of the crust at maybe stresses less than 200 megapascals, that coefficient of friction, okay, this here, it was about 0.85, and these rocks were mostly, I believe, granites and still pretty competent, harder rocks, again, but there was a pre-existing fault cut into the rocks. And then at higher normal stress, the coefficient of friction changed to 0.6. So Byerlee also proposed that I think with Brace maybe, proposed that stick-slip behavior, or earthquake, what was required for earthquakes in laboratory frictional experiments might be what's going on with earthquakes. And Jeff talked a little bit about what's required for stick-slip behavior, and he showed you the spring slider system where you've got this block, and it's got a frictional, the green area here is frictional resistive force. And if, as you pull, and you're restoring force, K, your spring constant, if there's actually two coefficient of frictions, if there's a static coefficient of friction when the block is stable, okay, and it actually reduces the dynamic friction is actually less once it starts moving, then you're going to have an acceleration of the block or your slip. Eventually it's going to come to stop and you're going to get your stick, and you're going to have a repeated stick slip behavior. And the conditions required are shown here, where this is your frictional resistance in the green, and if it falls off, if that frictional resistance falls off more quickly than your restoring force, your spring force, you're going to have stick slip behavior. So just in equation form. Okay, so the importance is that frictional stability is both a function of the actual friction on the fault, but also the properties K, which can reflect the elastic properties of the medium. So whether you're going to have earthquake behavior, stick slip, is a combination. Okay, so that was initial ideas about friction, but there was a lot of further experiments that were done by Dietrich and Ruina and a number of people, and they found out that your static coefficient of friction, by just having your block or your rock sitting in contact, the longer, there was a time dependence, that the longer they were in contact with each other, okay, the stronger the fault actually became. Okay, so here's a static coefficient of friction is increasing as a function of time. And the thought was that your fault surface has irregularities or little asperities, they were called, and that if they're held in contact for a longer period of time, there's actually some creep that will kind of flatten out those bumps, those irregularities, and increase the contact area for the asperities, therefore increasing its strength. So just having your fault contact under normal stress in contact for a longer period of time strengthen the fault.
Susan?
Yes?
Could you help me connect this equation to where you started with Byerly's data?
Michael, can you use the microphone since it's recording?
But that's not necessarily a good question.
Well, okay. Sorry.
The question.
Okay. Yes.
Susan, could you comment on the relationship between that equation and Byerly's original data?
So basically, we're now looking at how this, the coefficient of friction is behaving in an experiment when you're holding it there, so for a longer period of time. But at first, I don't think they were interested in how long, basically, I'm not sure exactly how the experiments work, but you put it under some normal stress, apply a shear stress, and see, under what shear stress it fails under a particular normal stress. Let's go back to this one, maybe.
Byerly measured μs, right?
Yes.
Okay.
Yes.
Without paying attention to time.
Exactly. So basically just under different conditions of normal stress, what shear stress did it take to produce failure, till it moved, till you produced, a motion. Then they realized people started doing experiments where they held, the fault in contact for a longer time. So we're just looking now at, and that the longer that you kept those fault surfaces in contact, the stronger the rocks became.
But Byerly is also, it's fracture and it's friction.
This is right now we're doing friction. He asked about fracture versus friction, and they're very comparable, except these experiments, they had already a surface, a pre-existing surface, so they're looking now at what shear stress it takes just to have motion across that surface, rather than to fracture, to create a new fracture.
I think none of these were actually creating new fractures, right?
No, these are all but if you look at, people think about Moore circles, right, and looking at fracture experiments where, you've all done Moore circles, right, that's, usually you're talking about fracturing new, you're not talking about fracturing new surface, okay, well.
Yeah. No, it all has to do with sliding friction, I think.
Oh, this does, but I don't know. Thorsten asked about fracture, so I'm not sure what. I think rock deformation. A lot of rock deformation experiments, you're putting in intact rock.
Yeah, that's true.
So that's fracture when you're breaking new.
I think in biology that was the case.
No, it wasn't.
Also pre-fracture.
Yeah. And you put gouge in it.
Right, but not yet, I don't think. I'm not at gouge yet. I mean, here. This time, if we're progressing in time. Okay, so the next thing, important addition to the experiments was to actually do them at different sliding velocities. Okay, and so what was noted was there was a velocity dependence on friction. So here is friction as a function of slip. So if starting with some initial velocity, you have a particular friction, and then in this case, velocity is increased. Okay, and what was found was there was an instantaneous, a very quick actual strengthening of or increase in friction that was followed by a slow decline over some critical distance dc. Okay, and here's an expression. So now we're looking at dynamic friction because we're actually having the rock is moving, and that this part of the expression describes this instantaneous increase, and this part is what's called the evolutionary effect, this decrease. Okay, where theta is a state variable, it kind of describes what the contacts look like, what those asperities look like, and what you need actually, and what I'm getting to is rate and state friction here. I'll just have this again. Is you actually also need an expression for how that state variable evolves over time. And there's different descriptions that people use of that. But the importance of rate and state dependent friction, okay, is that these coefficients A and B here, okay, that come from, they're shown here, are going to define these kind of transitions. So if, think about it here, okay, if A is less than B, which is shown here, right, and you actually end up with a friction that's less than what you started, then you will have stick-slip behavior, okay, and you can generate earthquakes. That's known as velocity weakening, because as you increase your velocity, your fault is actually becoming weaker. Okay, so A minus B, velocity weakening, stick-slip, earthquake generation. If A minus B is greater than 0, that's called velocity strengthening, that you actually ended up, right? You ended up at a friction value that is higher than you started at, and you're going to have just stable sliding. That's known as velocity strengthening. Okay, so we can now apply these concepts from state and rate friction back to the depth distribution of earthquakes. So here you see just a schematic graph of, that should be A minus B. I don't know. I forget. And here was the depth distribution. So a histogram, this is depth of number of earthquakes. And then stress drop just meaning positive, having an earthquake. So basically this transition from velocity strengthening, stable sliding, to velocity weakening, right, is where we start the seismogenic zone, where we can actually generate earthquakes, and then coming back out, again, making a transition from A minus B being negative to positive, having stable sliding, or at least coming out of that frictional regime. Okay, so if we try to apply those frictional transitions to the subduction zone, what do we see? Well, if we look up dip, I mentioned that we don't really see very many earthquakes on the plate interface, nucleating shallower than 10 or so kilometers below sea level. In many thermal models, that corresponds to temperatures maybe 80 to 100 degrees or so. So people thought that there might be some thermal control to this frictional transition. So some ideas were that you have a lot of sediments being subducted, brought down onto that plate interface, and that they may be undergoing some mineral transformations. Smectite to illite is one example, and at temperatures of 80 to 100 degrees, those begin, and that may be transitioning material from velocity strengthening, to velocity weakening. In addition, you've got a lot of sediments that are going to be being lithified and consolidated, and that process may be responsible for the frictional transition. I'm going to just show you a slide of some of the processes that have been postulated. This is from quite old, from Moore et al., but in that temperature range of 80 to 100, 120 degrees, there's quite a few reactions that they pointed out that could be strengthening your rock and therefore causing that transition from stable sliding. So either carbonate cementation or quartz cementation, pressure solution. I mentioned at least mineral transformations. So those are kind of the thoughts of what's going on at the up-dip edge for
Susan? Yeah. So what about this evidence that's accumulating that some subduction zones are not stably sliding at the up-dip end? For example, Tohoku, where you had this huge, stick-slip event, that encompassed the shallow part.
Right. I mean, I'm going to talk a little bit about that. I mean, you'll see I'm going to first start with this simple kind of model where there are these sharp transitions and then build from that. So can you hold to the question, and if I don't answer it, or is that okay? Okay. Yeah, so I'm kind of, giving you a little bit of a temporal evolution of thinking, and we didn't know that Tohoku could happen until it happened. So you'll see I'm going to kind of add complexity to this simple model. Okay, so what about the down dip? What are thoughts about why we transition from velocity weakening to velocity strengthening, or stick slip earthquake behavior to stable sliding at the down dip edge? Here, many people have pointed to temperature, and this transition tends to occur at different depths, maybe somewhere between 30 and maybe 50 or so kilometers for different subduction zones. And most people think that it corresponds to temperatures at maybe 350 degrees or so. It may be temperature related. Now we're going into viscous deformation. But there are some subduction zones that are quite cold that don't reach those temperatures until much greater depth. And for those subduction zones, it's been postulated that it's the contact with the mantle wedge. When the downgoing plate contacts the mantle wedge that we've talked a lot about being serpentinized, that signals this transition, that serpentine is velocity strengthening, and that would be in those colder subduction zones. It's the contact with that serpentinized mantle that would bring on that transition. So this is kind of the picture right here of the plate boundary, looking down on the plate boundary that I just presented to you, that we have up-dip transition, right, aseismic velocity strengthening to velocity weakening, what people call the seismogenic zone, where you could actually generate earthquakes, and then a down-dip transition. So this is a pretty simple picture. I mean, even when we were kind of drawing pictures like this, we did know that the seismogenic zone in here wasn't kind of just this uniform planar area that entirely broke during a large earthquake, that we had asperities, or areas that accumulated strain during the interseismic stage, and then generally during large earthquakes broke with most of the slip. Okay, so asperities, and we knew that we had, some bigger little ones, or potentially, and the thought was, the subduction zones that tended to have these large earthquakes. So I showed you in the first map, Alaska, Aleutians, a lot of the South American subduction zone, right? They had those big rupture areas. The thought was, well, they have just, the plate boundary there is made up of a lot of really large asperities that break in large earthquakes, and that some of the subduction zones that have maybe smaller earthquakes have, kind of smaller, different asperity distributions. We had some idea. Also, we realized that, yes, these are not really sharp boundaries, that there's, some variation, right, in where earthquakes start in depth, where they stop. So some things that we have to consider, and I didn't talk too much about, but we talked about when A is less than B, right, the frictional parameter, when A is greater than B. When A is very close to B, we have a frictional state that's called conditionally stable. And earthquakes don't nucleate in that region, but they can propagate. So some of the importance of that is if you have a distribution, let's say, of asperities like this. So let's say the asperities are corresponding to regions that are velocity weakening, and let's just say the white areas are velocity strengthening, or let's say they're conditionally stable, right? Then you can actually have slip nucleate here, propagate into this conditionally stable, and then trigger slip in this asperity. So you still, by introducing conditionally stable frictional properties, you can get quite a bit of slip and a large earthquake, even if you have this kind of, this type of asperity distribution versus just the large ones. So that's one important aspect of that. Another is that we recognize that at both a down dip and up dip, that this being conditionally stable is a condition for that is required for slow slip, so that we have slow slip occurring at these transitions, whether they're at the up dip, down dip, and within. And the seismogenics, I'm going to talk quite a bit about that. And we'll get to Tohoku. Tohoku could be a region where potentially we have a lot of conditionally stable material and maybe just a little bit of velocity strengthening, and that nucleated the earthquake and drove a lot of slip into the conditionally stable area. We'll return back to Tohoku and talk more about what's going on there. Okay, so kind of the best up-to-date picture now of what we think is going on the plate interface is shown here, where they're color-coded for their frictional behavior. These dark, I guess, red areas are the asperities areas that have velocity weakening friction, so where earthquakes can nucleate. The orange is areas of conditional, being conditionally stable, and then I guess the white is velocity strengthening, so it represented. It's not that we know the exact distribution. The idea is that it's very, very heterogeneous, that we even, we have some, right, even up very shallow, there may be some areas that are velocity strengthening, but if they're embedded in a conditionally stable area, we can have failure from these red areas driving slip into the orange areas, okay? So what I want to do now is kind of dissect this and actually first tell you what we've learned and why we've put this together and what we can do with it, looking at this main area, the seismogenic zone, where we have, mostly the velocity weakening and where earthquakes nucleate and propagate. Okay, then I'm going to move down here and talk about this transition. Okay, and that's where we'll talk a lot about slow slip. That's where mostly slow slip has been observed, right, at this down dip transition in subduction zones. And then we'll talk about the up dip transition and about whether we can propagate slip to the trench and what's going on at the up dip. Okay, so we knew even before, well, like as I said, before that most modern picture of what we thought the plate boundary looked like, or before we had this increase, this cluster of lots of large earthquakes which we could study, we knew some first order things about this, the main seismogenic zone. We recognize that big rupture areas seem to be segmented along a subduction margin, and that's, you can see that this is the Colombia-Ecuador margin, and these ovals are just the rupture areas of different earthquakes. So we recognize there are regions, like this shows the area of the 1906 megathrust event. It was a magnitude 8.5, and then within that area, between 1942 and 79, there were 3 smaller ruptures. But so not only is it segmented in 3 sections, but those 3 sections could potentially all go together. It's also the location of the 2006 magnitude 7.8 Ecuador event that occurred very recently. This is the Nankai region of southwest Japan, 2 very large, most recent earthquakes, but it has a history of either those 2 rupturing together or rupturing separately. So we recognize that there was a segmentation of the earthquake ruptures. And we also recognize that these events seem to have some kind of, semi-periodic recurrence interval, and that's well illustrated with Nankai, that there's some history that they repeat. But we didn't have very precise, we can show you rupture areas. Those are mostly determined by where aftershocks occurred after the large earthquakes for a lot of these historic events. We could not determine actually where the slip in that earthquake occurred. And so with modern instruments recording these large earthquakes, that's kind of the major advance. We can now, and I'll talk a little bit about how we do it, determine the precise slip distribution when a large earthquake occurs. Okay, so let's just look at what's our data that seismologists are looking at to obtain information about the source. Okay, we've got a seismogram. Well, it's displacement as a function of time. Okay? And what is it made of? Well, it consists of can be thought of as consisting of a convolution of many linear operators. One is the source. Okay, so how is the moment in that earthquake distributed as a function of time? And that's, when we want to determine the slip distribution, that's what we're after. To get that, we have to assume that we know these other 2 operators. Okay, so the source convolved with what's often called the Green's function. Contains all of the information about the propagation. So you're propagating an impulse from the earthquake to your station, and it has in it, the velocity structure, it has attenuation, things that potentially receiver function information. It depends on how we think we know it to at least first degree, or certainly we have to assume it when we're trying to invert our observation of ground motion for the source. So we assume that we know the structure, we can actually solve for impulse response from a particular location to our receiver. And then one thing we do know is the instrument, right? This is recorded. We record the ground motion through an instrument. We do know the instrument response. Okay, so if we do this, if we have seismograms and we can actually deconvolve the source, what we call the source time function, the distribution of moment release as a function of time, how do we get spatial information from that? Well, just to kind of give you an idea, this shows a distribution of source time functions around a particular earthquake rupture. And so if the earthquake started here is rupturing off to the right, what happens is kind of a Doppler effect, is that you have a much shorter source duration So this is now moment rate as a function of time. So the area under these curves is the moment. That has to remain constant no matter where you're observing it. But you see it as a much higher amplitude, shorter duration signal in the direction of rupture, a much lower amplitude, longer duration in the opposite direction of rupture, and then I guess what we call the true distribution of moment with time in the perpendicular directions. Okay, so we get information, spatial information from the shapes of the source time function. So how do we really do this? We embed the fault that slipped. We embed it into embed a grid onto the fault that ruptured. This is an example from the 2012 Nicoya, Costa Rica earthquake. I'll show you lots of examples because that's an area that I've done quite a bit of work in. But basically, we embed this grid. We can compute then the Green's function of the propagation from each of our grid points to our stations. We can then basically invert at each of those points for the source time function and obtain something like this, which, let's see, the coastline, well, I guess the coastline is over here, but this is showing that most of these grid points we don't have any moment release or any slip occurring, and we see that we have higher amplitude. These are little source time functions in this region. These are now moment is proportional to slip, so here we're showing them as slip, and we can then contour values of slip. In this case, then you actually look at, okay, how well does this model of the rupture match the actual observations? These are teleseismic P waves, but in this particular inversion, we also included strong motion, which is very close in measurements of actually acceleration is what they measure. And we also used high rate GPS, which is, again, GPS is measuring the ground displacement, but rather than just the final value at the end of the earthquake, we're actually including the whole time series of GPS ground motion. I didn't show that here, but okay, so we can, from inverting seismic waves, we can actually determine something about where the slip is occurring on the fault. I think Jeff showed you examples of how we do this in a very analogous manner with GPS data. So this is for the 2004 Sumatra earthquake, showing observed, let's see which ones, okay, observed are the, this is actual displacements during that earthquake, GPS displacements that were inverted for a slip distribution. So here's slip in meters for this earthquake. So we can actually compare what we get from inverting GPS and from seismic. Right now, we're also hopefully doing joint inversions, right? You want to, and I'll talk a little bit more about that. But what I wanted to illustrate is that this very large earthquake, we can see basically then how we interpret this slip is that we have some kind, these patches of very large slip are asperities, right? We have 1, 2, kind of 3 areas or asperities of high slip during this earthquake over an extremely long distance. I mean, these are latitude from, basically 2 degrees north to, almost 12 degrees north. Huge rupture area with huge amount of slip, 20 meters. Okay, this is a really great megathrust earthquake. Those are the kinds of values we're talking about. Okay, just think about 20 meters of slip, and actually maybe the average was 10 because there's patches that don't have very much, right? So maybe an average of 10 meters over that extremely large area. Okay, what's shown on the left is actually a comparison between this particular GPS inversion for slip and one done by Chuck Amen and all from seismic data. And what this is showing is moment, okay, as a function of latitude. So you can see you get a lot of moment here in this band. That's this asperity here, right? Something over here is these two asperities, and then this third one. And you'll see they match. So the black is the seismic, and the red is the GPS. They match really well in the beginning, and there's kind of not a there's some mismatch, right? Where the geodetic data is seeing more moment, which is more slip. And that's pretty common, I think, in comparing. Is that correct, Jeff? Geodetic and seismic slip distributions, that you often have more, the earthquake looks larger, the slip looks larger geodetically. And that might be that if you think about when these displacements often, and that these displacements include what we call afterslip, and I'm going to talk a little bit about afterslip. After the actual earthquake is done, the fault continues very slowly to slip. And so the geodetic data will pick that up, whereas the seismic, it's slipping too slow to continue to radiate seismic waves. But it's recorded on the surface displacements in GPS and not in seismic. And I'm going to talk more about that. But here I mostly wanted to, I wanted to mention that we can do this with two kinds of data, hopefully even integrating the two and getting even a better picture of slip, but that we can really determine now, slip in the along the plate interface and its distribution. I can show you. I want to give you an idea of how variable are slip distributions for these great megathrust earthquakes. I could show you a lot of maps, but you can actually see that by just looking at the source time functions. Let's say the average source time functions, ones that would be viewed from stations that are perpendicular to the rupture direction, or basically an average. And so this is showing seismic moment as a function of time for several different earthquakes. So we just looked at, in this slide before, we were looking at the spatial distribution of slip on the Sumatra earthquake. And that's this black line. So things that you can see, wow, it went on forever, incredibly long duration. You can see that the actual value of the moment rate is going to be proportional to the size of the earthquake, well, the area under the curve, just like I showed you before. So these are all very large earthquakes. Here's their magnitudes, but the style is very different. This one, had several asperities along a very long fault zone. If we look at the 64 Alaska earthquake, okay, that also is much larger in general, but had several asperities. Can you see these bumps? Along a shorter, time basically is proportional. Longer the earthquake goes on, the more the larger area that it ruptures. So just from looking at the time, we can see that Alaska has a couple of asperities. Tohoku, let's see, this red one is pretty simple. It's huge, right? But it's kind of looks like one pulse, right? And then Chile, we've got a couple other earthquakes. So there's a lot of variability. Okay, but we can actually, Jeff Abers, remember, showed us a seismogram, right? And he said you could see, he was trying to show us things that you could see just from the raw seismogram. And I think, although you have to do some work to get source time functions, you can learn a lot about earthquakes and the asperities and slip distribution from just looking at how the moment is distributed as a function of time.
Susan?
Yes. Yeah, the reason it's not on here is it's before, it predates, it predates seismic. It's a magnitude MW, which is based on the moment, 9.5. It's the biggest event, so it would be, way off this scale. Let's see. I'm trying to think of what we know about its temporal distribution. I'm not, do you know, Jeff?
It's not very well constructed.
Yeah.
as Susan said, it's not very well constrained. I think it looks a little bit like Tohoku, except it goes a long way in the right axis, so that the area under the area under the curve should be what, double, a little more than twice as much as Alaska. So it's a lot of slip. It's the amount of slip was consistent with what we saw in Tohoku, but the area was much larger.
Okay, so what can we do, once we know, okay, here's the slip distribution of an earthquake? I think one thing that I think is important and exciting is Jeff talked about how we can use GPS data in the interseismic stage, okay, between earthquakes, right, where the downgoing plate is dragging the upper plate, right, in that direction, and we can use that invert for locking on the plate interface. So we can compare then, we'd expect, if we know which parts of the plate interface are locked, can that tell us those exact areas are where we're going to have most of the slip in an earthquake? Can they tell us where the asperities in the upcoming earthquake are? And so I'm going to show you a couple of examples, because I think that the answer is pretty much yes, and we're getting closer and better at understanding more. So here's one example. This is the 2010 Mali earthquake. So these are surface displacements in the interseismic stage, right? They're in the convergence direction. Here's the trench. And these authors, Moreno and others, inverted this distribution for this set of locking, or this distribution of locking. So black is the plate interface is not moving at all. It's dragging the upper plate with it as it moves at the plate rate down to, I guess, the white, the lighter yellows and the white are just freely slipping. Okay, so this is the next slide is going to show a blow up. This is the epicenter of the 2010 Mali earthquake. And so the expectation, right, what if we could use this, if we could have some information before the earthquake on where most of the slip is going to occur, that's going to tell us also about where the strongest shaking will occur. And we'd expect, right, that we might have slip when that earthquake occurs, most of the slip here and here. So how well does this model of locking do to predict the slip distribution, the asperity distribution from either the seismic waves, right, or GPS during the earthquake? They both can be inverted for the slip distribution. So here, the locking is contoured. So here's this contour here, and here is 75% locking, okay? And that stays the same in all of these pictures. What changes is it's different people's models for the slip distribution using different data sets and different methods. So red is a lot of slip. This is 15, 17 meters in these red areas. So this model basically, this locked area here and here seems to agree pretty well. This one gets this bottom locked area pretty well. The top one not so well. This one doesn't really do either quite as well. So I wanted to show you that we're close, right? There's definitely a relationship between the locking and the slip distribution of the earthquake, but as variable as these slip models are for the same earthquake, I'm only showing you one model of the locking. If we had 3 models of the locking, they would probably vary a little bit too. So it's still, I think, I'm going to show you a couple more examples, but we're still, our ability to get, precise inversions for locking and for slip, there's still room for improvement to actually be able to look at this correlation and to feel really confident that we can, from a locking model, determine exactly where asperity or slip in the earthquake is. And things that, the things that affect it are sometimes you don't have the data coverage you need, but also Jeff mentioned what what's the planar surface. We know that these earthquakes are not occurring on beautiful planar surfaces. And that, knowing, and if we were able to actually tell what that 3D surface was, where the slip was occurring or where the strain was accumulating, that would help as well. So as we move forward and get more data and are able to do those things, I think we're going to get closer. I have to show you an event that I worked on. This is, again, the 2012 Nicoya earthquake. Now the Nicoya Peninsula is on its side over here. I showed you the slip distribution when I was just trying to illustrate how we determine these. So this is 4 meters of slip here in red. Here's the peninsula again on its side. This is actually a GPS inversion. So you can see, and red is also about 4 meters of slip. So they do agree very well, the geodetic and seismic inversions for the co-seismic slip. This black area right here was an area that was determined to be accumulating strain before the earthquake. And certainly this onshore patch of locking did break in this earthquake. And this event was a 7.6. It wasn't that, I'm still calling it a megathrust because it's about the biggest earthquake that occurs on this segment of the subduction zone. But yeah, you can see 4 meters of slip compared to, I was showing you 15 meters and 20 meters for these truly huge megathrust earthquakes. Okay, I just, to tie in a little bit with some of the things that Jeff said, remember he talked about, he showed you this slide, it's from his presentation. If you have a locked, this is just a model of a locked subduction zone. And he mentioned that this is the vertical GPS that you'd expect, and we usually don't see this subsidence in the interseismic stage when you've got locking and your plate is dragging the upper plate actually down to see interseismic subsidence. And I just wanted to show a beautiful example of Costa Rica because the Nicoya Peninsula sticks out so far close to the trench, you actually record very nice interseismic subsidence. So I just wanted to show you beautiful picture of the coast before the event was September 2012. So you can kind of see the palm trees. These are old palm trees. I mean, this is the intertidal, this region was land, and it's been being dragged down, and now you've got, dying palm trees and actual pretty fast coastal subsidence that was been occurring here. The earthquake happened in September 2012, and then after the earthquake, this is the same figure. You can see the uplift that this subsidence is mostly recovered during the earthquake deformation. So you can see this tower here, it's the same view. So it's just a nice example of your interseismic subsidence right near the trench, and then that area rebounding after the earthquake. So it's just kind of an aside. One thing that Jeff didn't get to talk about, and I think he wanted to, was at least after slip and post-seismic slip. I'm going to just focus on the after slip, but I'll mention something about, I guess, viscous mechanism. So after slip, it's very, as I mentioned, common after an earthquake, after the earthquake ends, fast slip ends and the seismic radiation ends. The fault continues to move in the direction of the earthquake. For subduction zone earthquakes, this is very common. I thought I had, let me see, I think there's supposed to be something there that's not showing up. I actually had GPS data to show this. Okay, but it's not there. So, but you can imagine, let's say, you're moving quickly in the earthquake direction, and then just as a function of time, you continue to move in that direction. I guess I don't have the GPS data to show you, but what I wanted to say about after slip is that generally, for megathrust earthquakes, tends to occur outside of the area that had most of the co-seismic slip. And this is an example, again, from Costa Rica. The co-seismic slip, most of the co-seismic slip occurred in here, and what's contoured is after slip. So this is amounts of after slip. It's only 6 centimeters. This is, I think, only a week after the earthquake. And then there's aftershocks that are on the plate that have been determined to be on the plate interface or superimposed. So We think that, that after slip in general, right, tends to occur kind of outside of the areas of maximum slip, and those are the regions that after slip is kind of triggering a lot of the aftershock activity. It's not really, that's commonly observed. It's not observed everywhere. There's, I guess, a lot of variability in the behavior. But so I'm trying to kind of summarize some that's been seen at many different megathrust associated with numerous megathrust earthquakes, but certainly not every one. Okay, so what about some surprises? And certainly the 2011 Tohoku earthquake was quite a surprise in that a lot of this is the slip distribution for that event. Here's the trench over here, right? And look at this number. I don't know why it's 62.9, but 63 meters of slip. And a lot of that is very, very, very shallow, close to the trench. I talked a lot earlier about why that area is mostly velocity strengthening, maybe conditionally stable. It's very unusual to have we hadn't really seen it before this, to have so much slip and most of the concentration of slip being at such shallow depth. And I don't know, there's quite a few models. Some people believe that it was driven into maybe the accretionary prism, and you have some geometric effects and surface effects. Some people think that, that those materials, they're not very consolidated, can in fact support that much slip. So it's kind of controversial. So I can't really tell you why that is. I don't know if Doug, if you wanted to add, or if any of the seismologists. Unfortunately, there's a lot of questions still open, and we don't really understand exactly how and why that happened. Okay, so kind of future for the asperity areas, where do we need to work and learn more? Certainly, as I mentioned, improvements in both our ability to determine which patches are locked before the earthquake, and improvements in our co-seismic slip inversions, maybe using more realistic, trying to incorporate, first determine. It's not that we're not using them. We don't know what the actual plate boundary, details of that plate boundary look like, trying to obtain that information and then do more. People are starting to combine data sets. And for these large earthquakes, and in the future, there's more and more data sets. I talked about seismic and geodetic, but even tsunami. We can record the actual tsunamis generated by these large earthquakes at, tidal stations and dart buoys, and incorporate that information. That's all part of, right? The source is generating all of that, the seismic waves, the surface deformation, the tsunami waves. It can all be integrated to produce potentially much improved slip distributions. Then, of course, once we even know them, let's say we know them really precisely, what are they? Jeff showed an example where it seemed like the lower plate and the lineations and the texture of the lower plate were kind of controlling where slip occurred in Alaska. I'd say, I'm not going to show you, but in Costa Rica, and I think there's other examples, people have pointed to the upper plate and properties of the upper plate actually controlling where the slip is occurring. We really don't know. And even if we can say lower plate or upper plate, that doesn't give us a mechanism. Right? We might be able to say, it's a correlation, it's not a causation. So I think there's a lot of work that could be done there. And then I think a big question is now we're starting to get examples of the same areas failing in 2 megathrust earthquakes. And can we precisely determine the asperity distribution to see if it even persists over 2 earthquake cycles? Does it, and potentially it would be nice to know if it persists over more than that. But I don't think we can even say for very many places that we have the same patches breaking in what looks like a repeat earthquake at this point. So I'm going to move on to the down dip edge. So I don't know, I mean, not that everything's changing, but that was mostly the kind of velocity weakening seismogenic area, because we're going to get into the conditionally stable, kind of really weird behavior. So if anyone wants to ask some questions now before we transition, I mean, absolutely ask them after, but.
Yeah, could you comment briefly on, like, you talked a little bit about rate and state friction, but could you comment on, for lack of a better way of describing it, but the rate dependence on rate and state friction? So, like, usually when we're talking about velocity strengthening or weakening, we're talking about changing the slip speed by a very small amount, but if we get up into earthquake slip speeds, then everything is velocity weakening, it seems.
There's still materials that's not the case. So it's that they actually become, when you increase the slip velocity, they become stronger.
Is there? Like when you get up to meter per second slip rates?
Well,
like the Toro compilation seems to show that everything drops down to a very low coefficient of friction compared with what it is at lower velocities.
I guess I'm not sure I can necessarily answer that.
Yeah, just add that the healing term, or the state-dependent term, also includes the ratio of the rates. So it does actually really, for steady state, which is the way that we commonly deal with it, it just depends on the parameters A and B, and A minus B. So it doesn't actually, the model still applies for seismic slip speed versus seismic slip speed versus plate motion slip speed, even though there's many orders of magnitude. So there are materials that do display velocity strengthening behavior, although exactly at what speed, how high you can drive those in speed is a good question, but we do see materials that behave that way.
So I have a question about the concept of the earthquakes stopping at sort of 10 kilometers depth, and also.
I didn't say they stopped. It's not generated, not nucleated.
Okay. So how much of that is possibly just due to the lack of instruments, since that's all generally offshore, and you would need to have an OBS out there to get the depth constraints?
Now OBS experiments, passive experiments, there's a lot of data, I think, and it's still pretty quiet on that. Except potentially sometimes splay faults maybe have events. I'm not saying it's absolute. I think there are some regions, and that's why I showed in that little model it had some red patches out there. So I think there are certainly observations of events on the plate interface that are happening at shallow depth. I don't think they're incredibly common. I guess that's.
And so, sort of related to that, then, with the Japan, with the slip, so much slip right at the toe, is it known for sure that hasn't happened in other earthquakes, or is it just that they had good pre-existing data?
I think with some of these very recent earthquakes, and actually people have been incorporating, doing models with the tsunami data, which has pretty good, constraints on shallow. Nothing like that amount at shallow depth. And I think now when I get to, talk about the shallow part, I hope I'll answer some of why that's not so common, and I'll tell you the slow slip. Even though most people have focused on slow slip at the down dip edge of the seismogenic zone, because that sits below land and there's lots of instruments. As we acquire information offshore on the seismogenic zone, we see more and more slow slip happening there. And I think that if you're slipping, you're taking up plate motion. You just don't have a lot of accumulated slip to happen in large earthquakes. So I think I'll get there. So maybe I will go on, because I don't want to end. I want to make sure that Jeff didn't get a chance to say as much as he wanted to about slow slip. So I don't want to leave it out. I noticed a lot of you were interested in it as far as potentially research topics. So I do want to make sure that I say as much as I can. So I want to go into this area first. I'm going to tell you both of these transitions. The story is a lot about slow slip. So let's first look at what observations have been made at the down dip edge. I think you all know what slow slip is. I just thought I'd show this one diagram. So it's slip that occurs much slower than earthquake. So if we look at slip duration, slip magnitude versus duration, right? These lines of constant slope or velocity. Earthquakes happen at, as you said, about 1 meter per second. Okay, plate rate is about 8 to 9 orders of magnitude less, right? This is at centimeters a year, and so slow slip is kind of in this range. I mean, a huge range of many orders of magnitude, but too slow to radiate seismic energy, but yet faster and usually happening. In an one period of time, not continuous, but maybe more episodic. Okay, how do we recognize it? I think Jeff showed an example. If we have a GPS, this is really recognized with GPS data because it's too slow to radiate seismic waves. So GPS, this is the strain accumulation in the direction of plate motion. We get a reversal for an earthquake. The time for an earthquake, even something as big as the 1960 Chile earthquake, would be 5 minutes. That's a huge, seconds to minutes in here. Slow slip, same motion, can even be the same magnitude. Maybe not as Chile, but up to, we've seen magnitude 7.2 magnitude slow slip events. So you get a lot of displacement, but it's happening over days, weeks, months. Jeff showed us an example of 9 years. If you believe the coral record, maybe 15 years in some cases. Huge range in the length of time. Okay. Jeff showed an example for Cascadia where it was first observed. Here are the black vectors, GPS vectors, are the strain accumulation. And then they're periodically reversed. That's these red by these slow slip events. Here's the actual record from this GPS station. I think it's a horizontal. So here's strain accumulation, slow slip, strain accumulation, slow slip, and it repeats. What also has been observed during these slow slip events, although we don't radiate seismic energy, there's what's been seismic tremor, which we think, people think now is maybe small patches embedded in the slow slip region that can actually have frictional stick slip behavior, and that you have a lot of them and they're going off kind of simultaneously and they're small, the slip is small, and you get this kind of more continuous, and I'll show you what it looks like, kind of relatively noisy tremor, but it correlates across many stations in an area. Okay, so here's what tremor looks like, at least looks like in Cascadia. So this is at about an hour or so of tremor at seismic stations along this margin. So the stations range over a couple hundred kilometers. So when you see, if I just looked at one of these records, I'd say, oh, it's wind, it's, I don't know, a bus going by, well, not a bus, or a train, a long train, or whatever. But the fact that it looks the same at stations that are hundreds of kilometers apart are telling you it's something, it's the Earth, okay? To be able to see those signals at that distance. So tremor doesn't look very good. In fact, the way that in Cascadia it's located is that these records, the envelopes are made of the energy, and they're correlated at the different stations in small time chunks. And if you get correlations in that time chunk, you say, okay, we've got a tremor detection, then you look at the offsets. You assume that these are S waves, and that the offsets at the different station are due to travel time differences, and you can use those travel times to actually locate the little packets. So maybe 3 minutes or 5 minute packets are located, and they're given a little white circle. So that's in Cascadia, and that's automated. You can go to the website, and you'll see anytime tremor's happening, there's a updated, just like an earthquake catalog, there's a tremor catalog. And it's done from taking envelope correlations of these waveforms, and you get these white dots. Okay, so that's the tremor. This is one particular slow slip event, and the contours are the slip. At Cascadia, these events last, I'm trying to remember now, a couple of weeks, and they occur about every year or 14 months. So they're pretty regular. This is one of them. You can see where the slip is occurring. It's over a pretty large distance, a couple 100 kilometers, and tremor is associated with it. Okay, so that's Cascadia. It's also was early. It was discovered very early. Both the tremor actually was first discovered in Japan, and then later the slow slip events there. So if we go to southern Japan, here's Shikoku. This is black circles here are just normal earthquakes. The red are tremor. What David Shelley did, so here's some ugly looking tremor from stations here in Shikoku. So you see the same kind of packets of energy. They don't seem to correlate quite as well, but so what David Shelley did was he focused in looking, and here's a blow up of just this little packet here at the several stations. And he noticed that, well, I actually can see almost an S wave. And what he did was use these waveforms at the different stations as a template, and he ran it through the continuous time, and he found lots of matches. And then he stacked those matches and actually got even nicer looking S waves. And in fact, when he stacked them, out of the noise came a P wave. And so he called, well, I'm trying to think of who the first, no, actually Japan first named these low frequency earthquakes. So he could actually find earthquakes in the tremor, low frequency, because if you look at their spectra for earthquakes of this size, they actually were devoid of the higher frequencies that normal earthquakes of similar size should have. So they were called low frequency earthquakes. So he found low frequency earthquakes. That's what is plotted here for one slow slip event in Japan. And this is plotting both the normal earthquakes and the tremor on a cross section, A prime, of what you see is this is the VP-VS ratio. So what you first notice is the blues here, the high VP-VS ratio is been interpreted as the slab, that there's fluids trapped in the upper part of the slab, and that's giving it the high VP-VS ratio. And then can you see this band of even highest ones is associated with the tremor. In fact, these events are interpreted as being in the plate. They're intraplate events. I think even there's some mechanisms for them. Whereas the low frequency earthquakes are on the plate interface. And later people actually were able to determine some focal mechanisms for these events to confirm that they're occurring on the plate interface. So occurring on the plate interface, at the down dip edge, in an area very high VP-VS. So here's kind of their interpretation. You've got the locked, so the tremor is occurring at the down dip edge of the locked area, very high pore fluid pressure, at the corner of kind of your mantle wedge. And they interpreted these really high VP-VSs as having to reflect high pore fluid pressure. They really couldn't get that really high VP-VS with in compositions or in any other way. And so the idea, I guess, even though they didn't really say it, was that these high VP-VS actually reduced your effective normal stress and kind of allowed some frictional motion. So these little teeny patches embedded in the slow slipping area could actually have frictional motion. Japan has a very similar, Japan and Cascadia are really very similar at their down dip edge. I didn't show in Cascadia, well, actually that was Japan, but okay. Both of them have locked areas, right, up dip. This, for Japan, that same area, here's the locked region that broke in these two large megathrust events in the 40s. The reds are the zone of tremor and pretty short-term slow slip events. So short-term is only a few days. They don't really see them in Japan with GPS. And I don't know, Jeff, maybe now they started to. No, they see them, they have strain meters, they have borehole strain meter, a network of borehole strain meters that actually show these slow slip events that are occurring in the same, along this band of tremor. But they're too small to actually be seen and too deep, I guess, to be seen on the surface GPS, which is covered. I mean, they have great GPS coverage here. But they do have short-term slow slip events with the tremor. Again, they only last a few days. They also have observed long-term slow slip events, and they locate those in these areas of blue circles. Those are seen on GPS. So they last on the order of months. So they're larger, they last longer, and they're actually up dip, right, of this band. Now in Cascadia, they have not observed these short-term slow slip events, but they've seen a gap between what they think is the down dip area that's locked, okay, in Cascadia, and the tremor and short-term slow slip events. So they haven't seen it, but they have a gap. It hasn't been filled in yet by these long-term. I think they're still looking for them. They're thinking they're going to find them. And just in a very recent paper, it came out this year, Gao and Wang kind of tried to explain this banding. Okay, so the banding is the deepest, is the ETS, the episodic tremor and slip, or the short-term slow slip events and tremor, right? And then in Cascadia, it's a gap, but in Japan, it's long-term slow slip, and then you going up dip into the seismogenic zone. So how did they explain this?
Susan?
Yes.
About 5 minutes.
Okay, so I want to go to the up dip, so I'm just going to, okay. What they basically think that this happens only in very hot subduction zones, so that you actually, you basically transition from frictional to more creep at a depth that's shallower than the mantle wedge. Okay, so that's your reason for going from basically having earthquake rupture into this creeping regime. But, okay, so here's the cross section. Okay, but so that's explains that. Then you go into this ETS regime because of an increased pore fluid pressure, decreased effective stress, because you have fluids coming off. You're hot enough, you've got your basalt eclogite and fluids coming off that serpentinize the mantle wedge. With changing to serpentine, there's a volume increase. So you're actually increasing or decreasing the permeability by increasing the volume. Let's see, you also have, because of that, some fluids migrate along the plate interface. They can't get out. So some of them migrate here, okay, and actually deposit silica in this corner. So you've really created a very low permeability seal and very, very high pore fluid pressures here. And that actually allows you, these are some of their experiments, but it allows the frictional, it allows you to actually have your frictional strength be less than or have it be more efficient than ductile deformation in this very small range. And so you can actually have tremor and frictional behavior in there. I read the paper quickly. It's interesting, but we definitely have the observation. The observation's there, the explanation. Okay, in the next few minutes, I just want to talk a little bit about up dip area, because Jeff mentioned that in Peru, okay, we need offshore measurements. This is GPS, predictions for GPS, if you had locking all the way to the trench or not. And, you know, onshore measurements doesn't matter. All these models don't diverge of whether you have a lock to the trench or not until you get very close. In Peru, they have 2 observations that fit a locked model. So I want to just show you 2 places where we definitely have slow slip at the trench and you know, not locking. One is Costa Rica. Let me just see. There's a lot of slow slip events. I'm going to show you a movie quickly of slip distribution as a function of time. These are again, slow slip. So you looking at the reversals in the GPS, right, that occur over a long period of time, you just take you basically invert the GPS as a function of time during those slow slip events. So let me just show this. Well, I can't, I can't show it, what we see, and this actually we have offshore. I guess the important thing is we have the peninsula close to the trench, but we also have data from, there are boreholes out here, 2 boreholes that actually have formation pressure sensors and ocean bottom pressure sensors. So they're inverted together with the GPS to see quite a bit of slip. This is during one slow slip event. A lot of slip down dip kind of migrates around. This is the locked area that I showed you, the asperity for the 2012 event. So we have a lot of slow slip happening at the trench. Don't think it's locked. One other area that I've been involved in is a project Hobbit, Sikarangi Ocean Bottom Investigation of Tremor and Slow Slip, where ocean bottom pressure sensors were deployed to capture one of the slow slip events that happened. We were hoping to capture this event in 2014. We put the instruments out before, and in fact we did. And so this is some ocean bottom pressure data. You kind of correct it for oceanographic effects, and you can invert that data for slip. That's these contours, and we get slip, this is 5 centimeters, very, very close to the trench. So there's some subduction zones, I guess, where we have, and there's very few that we actually have any kind of shallow offshore geodetic data. The 2 that I've been involved in where we actually have that information show that we have a lot of slow slip occurring. In fact, we have enough slow slip. If the periodicity of these slow slip events go back, we have 10 years or 15 years and they happen every year or 2, if that's been going on, they can account for all of the plate motion. So there's no strain being accumulated by the trench. That's really important for predicting kind of tsunami hazard, right? If you have no accumulated strain, shallow strain, when an earthquake does happen in the deeper area, it's not going to slip, right, to generate a tsunami. So there's a lot of important information.
Susan, do those slow slip events near the trench also give tremor, or is the only...
Yes, no, they do. They are tremorgenic. And
so it'd be possible then, in the absence of seafloor geodesy, to perhaps infer their existence from the tremor.
In fact, these are tremor, and this is seamounts. This is in New Zealand, but these dots are tremor, and Costa Rica is very, very tremorgenic. It's kind of all. Well, one thing I will say is so it doesn't follow the slow slip like Cascadia or Japan. It's temporally very, very correlated, spatially. It's either we can't locate it as well, or it doesn't have that same relationship. I may then leave this. I know Jeff wanted me to talk a little bit about, so I'm going to I still have a couple minutes. Let me just close on earthquakes and slow slip. This is an important bringing it all together. Okay, so
try to close it in a minute or 2.
I think I can. This is my last. I'll just talk about this one. Okay, so people have asked, are earthquakes and slow slip phenomena the same, different? And they have different scaling properties. So let me just show you that this is and I think Jeff showed this. This is duration of your event, right? Huge, many, many orders of magnitude duration, right? From, you can see, seconds to years versus magnitude of the earthquake. Earthquakes, all of the earthquake phenomena are showed, fall along this line, okay? And that relationship, let's see, is that the duration of these seismic, events scale as the moment to the 1/3. And let me just say where that comes from. I never said this before. Moment, seismic moment, we talked a lot about it, is equal to the shear modulus times the area that slips times the amount of slip. So it's proportional. Moment is then proportional to length cubed, right? Area times slip. Well, the length that an earthquake will slip is constrained by, it's equal to its rupture velocity times the duration. And for earthquakes that generate seismic waves, the velocity is constrained by the speed that seismic waves propagate, the S wave. So they're quasi-constant, okay? So therefore, length is proportional to distance if velocity is constant. And I can sub in that length for distance and see that moment is proportional to distance cubed. And that's where this distance, right, proportional, this relationship comes from. Okay, it's constrained by seismic waves being generated by the earthquake. Well, slow slip don't radiate seismic energy, so they don't have this constant velocity constraint. So they don't have to fall on that line, and in fact, they don't. This is the low frequency earthquakes that make up tremor. These are some of them, here are the short-term slow slip events, long-term slow slip events. This is actually, I think, I don't know if Jeff's value isn't on here right yet, but his 9-year, and this is the 15-year coral value. So they follow a very different scaling law. And so people believe that the physics that control them is very different from earthquakes. There's some models out there. There's a lot more models being proposed. I think it's a really important aspect. We don't really understand. So I think, I think with that, wow, I'm going to end here with this picture that things are complicated, okay, right? That there's different slip modes that are, and it goes back to the geology. Look at this. If this is what's found in that plate boundary, you've got areas that have frictional slip embedded in areas that have different properties that are probably creeping. So we have a whole spectrum of, slip processes.
Okay. Do we have some questions from students and postdocs? Oh, come on, students. Did you have too good of a 4th of July or what? Over there. Yeah.
I have a really simple question. There's a slide early on where you showed the beach ball solutions, CMT solution, and it had dots on it. Can you explain what those dots are?
I think the dots might have been where the stations are located. So basically it's a takeoff angle and azimuth. So a lot of times you like to see the distribution of where your actual stations are.
Within the beach ball?
Yeah, the beach ball is a lower hemisphere projection of planes. And so you can also project, because think about, have you done first motion? If you do first motions, you have to put your positions, right, of your stations, and then you either say, is it a compression or a dilatation? So you put them on then remember you have to draw the planes that separate the compression from the dilatation.
And students don't do that anymore.
Yeah. Anyways, he's shaking his head, but maybe he doesn't. But yes, I mean, I'm not positive, but I think I remember I had one mechanism that did have dots in it, and that's what it was.
Yeah, over here.
If we're talking about slow slip events that are on rates of years, decadal, and even at plate convergence rates, at what point do you call that slow slip versus creep? Well, I think this is something that, since Jeff might want to answer, but it's still, I guess, transient, episodic. I mean, you can actually see a start, right, and maybe you haven't, I don't know if you, and an end, but it's certainly moving in that direction, I think.
I think that's a good answer. I mean, we don't know.
Yeah.
It's a definition, matter of definition. So, when you see things that have starting and ending points, that's an event. When you have things that are going on continuously beyond the whole scope of your data, you don't necessarily know if that's a really long duration event or something that just always happens.
I mean, I think to some degree, slow slip may be occurring in lots of places. Slow slip meaning an acceleration for a little period of time, and then maybe a slowdown, an acceleration. Many different parts of the plate interface kind of continuously, but yet I guess it's still an acceleration. It's still not a steady creep. But
other questions from students, postdocs?
So you say that you've observed the places where you observe shallow slow slip. You think that they can mostly accommodate the plate motion, but then from Tohoku we also see that there's a huge slip in the shallow region. Is there any difference between the different subduction zones? And do they see slow slip events that are shallow in Japan?
I mean, Tohoku, let me think what the latest, I mean, I've heard there's some very anomalous, or I don't know if it's anomalous, but a particular clay that was coating the plate interface. Donna's shaking her head, so maybe she can help me out here. That, you know, it was a little bit unusual, or it's not found in that many other places that allowed that type of frictional behavior. And I'm certainly, I guess what I really want to leave you with, I know I tried to summarize observations to say some generalities, but maybe that was the wrong approach. I don't know how many generalities we really can make. There is so much variability in slip behavior in the up dip edge, the seismogenic zone proper, the down dip edge, that maybe I chose to organize things not as well. I mean, I don't know if we, I mean, I'm beginning to question whether we really can say this is how a megathrust earthquake works. And you know, there's some, I think the variability might be so much larger maybe than what is in common sometimes. So I don't understand Tohoku. I would not expect Tohoku event, and I could be wrong. I mean, and this is recorded too, so I would not expect a Tohoku event well, I can say this pretty sure because it's not this slip right in New Zealand or in Nicoya Peninsula, Costa Rica. There's just no slip, nothing's being accumulated there. It's all going in these these episodic slow slip events. I don't remember I don't know if we had a model for strain accumulation. I don't think we could have that close to the trench in Tohoku, because you'd have to have, seafloor geodetic measurements. I don't think we had that. So I guess my one hope is that if we do and when we get there, we'll see that there is some strain accumulating in in the shallow portion and be able to have some idea that we can generate an earthquake like that.
Yeah. Okay, sure.
So regarding Tohoku, I guess the question about whether it's creeping or locked is different from how much a stress does it have near the trench. So maybe it's creeping, but it still have high stress. And that stress can be released when you have very high rate. As the first question get asked, you have high rate, you get additional dynamic weakening effect, like thermal pressurization or even melting. I guess not melting for this case, but you get some additional dynamic weakening effect, which will help you release that stress in a very short time, which will radiate seismic waves. So I think that may be an important factor to understand this anomalous Tohoku shallow sleep.
But I think Susan's point is that if it's creeping, as it seems to be doing in New Zealand or Nicoya, then there won't be any slip deficit in the shallow part. Well, if you don't have a slip deficit, you're not going to have much slip during the main earthquake. Yeah.
So there is a strange material at Tohoku.
Thank you.
Just to follow up, it's a brown clay.
Right.
It's only about 1 meter thick. It's not clear. That's the interface, but it's extremely weak. And Casey Moore has mapped it. It's actually a mappable unit across much of the Western Pacific, and so you'd predict it occurs some places and not. And I think Casey was trying to argue that controls slip behavior.
Okay, I think we've transitioned to senior people. So Donna over there.
I have the mic, so I get to go now regardless. I guess it's a general question for everyone, but I thought that some of the models for shallow slip during Tohoku involved dynamic overshoot. And so in those cases, would you be able to anticipate the amount of shallow slip based on strain accumulation in that area beforehand?
I mean, I think I still kind of go with what Doug was emphasizing. I think you may have some. So but if you really have no strain accumulated, I don't know how much slip you can get from some of these, stress accumulation and overshoot. It just doesn't seem like much. But I'm not going to say nothing.
I mean, the weird thing about a Tohoku is that the most slip happened near the trench. So it wasn't like the area near the trench was dragged along by the main rupture. It actually had the most slip near the trench.
But I don't think we can say that that area has been creeping. I don't think we have evidence for slow slip and mostly creep in that area before the earthquake.
I feel like your couple of your first slides I thought were kind of reminded me of some things that I had not been thinking about for a while. And I think the last student comment, if I feel like, is on target on this. We've thought a lot about the stability criterion, A minus B, and basically have something that's velocity strengthening, but it's still a frictional process that is dependent on the absolute value of the friction on that interface. And so you could have a steadily creeping region that has a high coefficient of friction on it, and so it's still it'll have it basically has small creep events associated with it, but it still maintains a very high stress. And so you can have, its steady state condition is something that's got relatively high stress across it, that's put on the plate boundary and maintained over very long time periods. And it's sort of jittering, but because it's a high strength fault, it stays stressed. And then you have a big event comes through that dynamically weakens it through whatever dynamic process we don't quite understand yet at those really high driven slip rates, and it suddenly can release that stress. So it feels like I guess my question to you that I was going to ask was, is there a lot of conversation going on right now that I haven't actually, I'm a little bit outside this field. Is there a lot of conversation going on that's really thinking about the interplay, not just of conditional stability, whether A minus B is plus or minus, but also what the overall strength of the material is on the fault? And I think the other slide that you pointed out was it's also very dependent not just on the frictional properties, but of the elastic properties of the medium it's sitting in. So
I would say I have not seen very much. I mean, I hope maybe things are moving that way. I made that point, although I can't back it up with a lot of research where has kind of pursued the K as opposed to the the A and B of friction. And I don't know if Tohoku is pushing people. I haven't been. I read all the. They're coming out very quickly, kind of trying to explain models, and I'm not as up to date as maybe I could be. So I don't know if somebody else wants to comment on that particular point. I think not, is my general feeling.
Jeff? Yeah, just an observational note. There were a couple of places where they had offshore seafloor geodesy before the event. And these were, I think, maybe halfway between the trench and the coast. So they didn't really constrain what happened at the toe. But those data actually were consistent with a locked zone that extended, pretty far up dip. But of course the resolution was still lacking at the trench. So that question of where the slip maximum was and whether that was something that was locked before is still open, I think. But Japan basically intends not to have this be unknown in the future. So they have a massive program of seafloor geodesy that is essentially aimed at determining whether the faults are locked out to the trench or not. Because they want to know for future hazard assessment. And so before too long, we'll know that answer, I think, pretty well from Japan. We won't know it anywhere else because nobody else is willing to spend the money to do it.
Okay, I think with that, we're going to have to go to coffee break. So thank you, Susan.
Stock's answer. He's just proud that he knows, right? Because, but does anyone recognize who this is? Yes, okay, yes. He worked at the USGS and he did a huge number of experiments on friction. And these experiments were very similar to the rock deformation experiments that have been talked about, except when actually putting the rocks under normal stress, there was a kind of a cut already made in it so that slip would occur and failure on a pre-designated surface. So he did experiments basically under different normal stresses and applied shear stress and saw how much shear stress it took for failure. Okay, so here's normal stress, shear stress on the y-axis, normal stress on the x-axis, and what he found, and this is called Byerlee's law, okay, that there's a linear relationship, and that the slope tends to change, that this coefficient in the shallower parts of the crust at maybe stress is less than 200 megapascals, that coefficient of friction, okay, this here, it was about 0.85, and these rocks were mostly, I believe, granites and still pretty competent harder rocks, again, but there was a pre-existing fault cut into the rocks. And then at higher normal stress, the coefficient of friction changed to 0.6. So Byerly also proposed that, he, I think with Brace maybe, proposed that stick-slip behavior, or earthquake, what was required for earthquakes in laboratory frictional experiments might be what's going on with earthquakes. And Jeff talked a little bit about what's required for stick-slip behavior, and he showed you the spring slider system, where you've got this block, and it's got a frictional, the green area here is frictional resistive force. And if, as you pull, and you're restoring force, K, your spring constant, if there's actually two coefficient of frictions, if there's a static coefficient of friction when the block is stable, okay, and it actually reduces the dynamic friction is actually less once it starts moving, then you're going to have an acceleration of the block or your slip. Eventually it's going to come to stop, and you're going to get your stick, and you are going to have a repeated stick-slip behavior. And the conditions required are shown here, where this is your frictional resistance in the green, and if it falls off, if that frictional resistance falls off more quickly than your restoring force, your spring force, you're going to have stick-slip behavior. So just I hope everybody had a good 4th and yesterday. So today I want to pick up on a lot of the topics that Jeff talked about on Monday about properties of the megathrust, and I'm going to hopefully give you a more seismological perspective. So, you know, title Megathrust earthquakes. Megathrust earthquakes are events that occur at the plate boundary at subduction zones. And the mega, you know, generally we're talking maybe about events 7.5 or larger. And if we look at where around the globe these events occur, here it's showing since about 1900 all the largest earthquakes, where you see black blobs is where we actually could determine something about the rupture area. So what, you know, what length and distant width on the subduction zone actually ruptured. And the bigger the rupture area, the bigger the earthquake. When there's not that information, you'll see X's. But do I have a pointer? Oh yeah, here. Is this a pointer? This. Okay. So, you know, you can see that along the subduction zone in South America, Alaska Aleutians, into Kamchatka and Japan, we have a lot of very large earthquakes. But if you go look at the Marianas and down here in New Zealand, there's a dearth of large events. So we'll get back to that. There's also not a uniform distribution of these events in time. So here is a map again since 1900 of these large, mostly megathrusts. These are the largest events since 1900. So they show focal mechanisms. Not all of them are megathrust on the subduction zone plate boundary, but most of them are. So everything in both green and blue, but the blue, the beach balls, the actual focal mechanisms are just those events that occurred in this 10-year period, 2004 to 2014. So there's really been this explosion of large megathrust earthquakes in the last decade. And that's much more clearly shown in this plot here of magnitude of events versus a year. So, and here below is cumulative moment versus year. Okay, so we can see, let's go back in time, that late 1950s through the end of the 60s was another kind of surge or cluster of very large earthquakes. And then things got really
relatively quiet for a couple of decades, and then starting with the 2004 Sumatra earthquake, another kind of burst of activity that's continuing through today. Now, I did my PhD work kind of in here, in this period of nothing going on. So I spent a lot of time actually studying these very large earthquakes that happened in the 50s and 60s. And if somebody asked me, well, even asked me up until 5 years ago, whether there was some kind of, why are there these clusters? Can an earthquake that happens in Chile actually affect or bring closer to failure or loss? They had already a surface, a pre-existing surface, so they're looking now at what shear stress it takes just to move, have motion across that surface, rather than to fracture, to create a new fracture.
I think none of these were actually creating new fractures, right?
No, these are all but if you look at, people think about Moore circles, right, and looking at fracture experiments where you've all done Moore circles, right? That's usually you're talking about fracturing new. You're not talking about fracturing new surface. Okay. Well.
Yeah. No, it all has to do with sliding friction, I think.
Oh, this does, but I don't know. Thorsten asked about fracture, so I'm not sure what. I mean, I think rock deformation. A lot of rock deformation experiments, you're putting in intact rock.
Yeah.
So that's fracture when you're breaking new.
I think in Biology that was the case.
No, it wasn't.
Also pre-fracture. Yeah. And he put gouge in it.
Right, but not yet, I don't think. I'm not at gouge yet. I mean, here. This time, if we're progressing in time. Okay, so the next thing, important addition to the experiments was to actually do them at different sliding velocities. Okay, and so what was noted was there was a velocity dependence on friction. So here is friction as a function of slip. So if starting with some initial velocity, you have a particular friction, and then in this case, velocity is increased. Okay, and what was found was there was an instantaneous, a very quick actual strengthening or increase in friction that was followed by a slow decline over some critical distance dc. Okay, and here's an expression. So now we're looking at dynamic friction because we're actually having the rock is moving, and that this part of the expression describes this instantaneous increase. And this part is called the evolutionary effect, this decrease, okay? Where theta is a state variable. It kind of describes what the contacts look like, what those asperities look like. And what you need actually, and what I'm getting to is rate and state friction here. I'll just have this again. Is you actually also need an expression for how that state variable evolves over time. And there's different descriptions that people use of that. But the importance of rate and state dependent friction, okay, is that these coefficients A and B here, okay, that come from, they're shown here, are going to define these kind of transitions. So if, I think about it here, okay, if A is less than B, which is shown here, right, and you actually end up with a large earthquake in Alaska, I would have said absolutely not, that's crazy. Now I'm not sure how I feel about that, but there are absolutely some people who think that the seismic waves that are generated from these big earthquakes that travel around the globe actually can change the stress state at distant plate boundaries and actually bring them closer to failure, and that
there may be super cycles of these earthquakes, this being one and we're in another now. Now, I'm not going to talk more about that. It's interesting. There are some papers about that. But I am going to use the fact that we have this amazing number of large earthquakes that have occurred when geophysical instrumentation was really exploding, and that they're really very, very well recorded. And we've learned a tremendous amount about megathrust earthquakes from that data. So what I want to do today is to really try to synthesize what we've learned from studying those recent large earthquakes, and then try to discuss some, obviously we always have outstanding questions and directions for future research. But before I do that, earthquakes are a frictional process, and we've talked a lot in here, and I'm going to continue to talk about rheology, mostly kind of rheology of the deeper part of the Earth. So I wanted to spend a little time and talk about friction and its relationship to earthquakes. So it's been observed for quite a while from continental earthquakes that they don't seem to happen near the surface of the Earth. So this is a distribution, it's a histogram, so number of events versus depth for earthquakes in Parkfield. And there's maybe a few events near the surface, but in general, earthquakes don't seem to start in the continental crust. And this is still kind of true today till maybe 3 or 4 kilometers. And then, you kind of have some kind of distribution, a peak, and then they end in continental crust somewhere about maybe 15 or so kilometers. And that's analogous in subduction zones. Here's a little cartoon of a subduction zone that we also don't observe many earthquakes happening shallower than maybe 10 or so kilometers below sea level. And we have a lot of earthquakes in I'll term the seismogenic zone, and then we transition again out, not having earthquakes. So we see an analogous transition. And so, we see some kind of aseismic behavior, which is believed to be, stable sliding. We know the plates are moving, so we're accommodating that motion somehow. Creep and stable sliding, transition into some kind of unstable seismogenic zone, and back out. So, let's see okay, so these are frictional transitions, and this man was very important in doing a lot of experiments on friction and helping us understand these types of transitions. And again, in the spirit of famous scientists. Oh, you're right, but oops, I'm sorry, laser. But I thought we had students in post equation form. Okay, so the importance is that frictional stability is both a function of the actual friction on the fault, but also the properties K, which can reflect the elastic properties of the medium. So whether you're going to have earthquake behavior, stick slip, is a combination. Okay, so that was initial ideas about friction, but there was a lot of further experiments that were done by Dietrich and Ruina and a number of people. And they found out that your static coefficient of friction, by just having your block or your rock sitting in contact, the longer, there was a time dependence, that the longer they were in contact with each other, okay, the stronger the fault actually became. Okay, so here's a static coefficient of friction is increasing as a function of time. And the thought was that your fault surface has irregularities or little asperities, they were called, and that if they're held in contact for a longer period of time, there's actually some creep that will kind of flatten out those bumps, those irregularities, and increase the contact area for the asperities, therefore increasing its strength. So just having your fault contact under normal stress in contact for a longer period of time strengthen the fault.
Susan?
Yes?
Could you help me connect this equation to where you started with Byerly's data?
Michael, can you use the microphone since it's recording?
that's not necessarily a good comment.
Well, okay. Sorry.
The question.
Okay. Yes.
Susan, could you comment on the relationship between that equation and Byerly's original data?
So basically, we're now looking at how this, the coefficient of friction is behaving in an experiment when you're holding it there, so for a longer period of time. But at first, they weren't. I don't think they were interested in how long. basically. I'm not sure exactly how the experiments work, but you put it under some normal stress, apply a shear stress, and see, under what shear stress it fails under a particular normal stress. Let's go back to this one, maybe.
Byerly measured μs, right?
Yes.
Okay.
Yes.
Without paying attention to time.
Exactly. So basically, just under different conditions of normal stress, what shear stress did it take to produce failure, till it moved, till you produced, a motion. Then they realized or people started doing experiments where they held, the fault in contact for a longer time. So we're just looking now at, and that the longer that you kept those fault surfaces in contact, the stronger the rocks became.
But Byerly's also, it's fracture and it's friction.
This is right. Now we're doing friction. Oh, sorry. He asked about fracture versus friction. And they're very comparable, except these experiments